everyone. So we'll continue our discussion with the mathematical preliminaries chapter, and just to point out here, we had been discussing in our previous part of the lecture on the rules of index notation, and the plan was that we would be applying these rules to something which is very familiar to us in the form of the dot product. So we'll continue our discussions with dot product. But before we can actually launch into a discussion of dot products and how the index notation may be applied there, we first take a look at the unit vectors themselves. So we know for a fact that if we have a unit vector like this, E1, and it is dotted with itself, we know very well that this is equal to 1. Now, I hope that none of you will be feeling uncomfortable with this kind of a notation for the unit vectors, because most of you may be more familiar with the I hat, j hat, k hat notation, but this is exactly like that. Okay, so you may, for starting out purposes, you may think of that E1 hat is like the I hat, and the E2 hat is like the j hat, and the E3 hat is like the k hat. But this is certainly more general, and we should familiarize ourselves with this kind of a notation. Further along, if we take the dot product of the E1 hat with the E2 hat, we know that this is equal to 0. All right. Similarly, if we proceed like this, we will find that E2 hat dot E3 hat is equal to 0, and so on and so forth, and E3 hat dot E3 hat is equal to 1. Now, if we want to represent all of this information at one shot, we can write something like this, that EI hat dotted with EJ hat, that is equal to 1 if I is equal to j, and 0 if I is not equal to j. So this one statement encapsulates within it all the information present inside whatever we had written in the earlier step. Okay, now this particular statement can be written in a further shorthand notation using something which is referred to as the Chronicle Delta. So we write it like this, that EI hat dotted with EJ hat is equal to delta IJ. Okay, so this delta IJ is called the Chronicle Delta. Okay, now it is important to note that despite what we had been discussing in the previous part of the lecture, so if we go back quickly to this previous page, we had said that the number of free indices denotes the order of the tensor of that term. Now, that should not give us a wrong impression that here we have I, I is one index and j is another index. In total, this entity has two free indices, so this is a tensor of order 2. This is wrong. Okay, that impression would be completely wrong, because you understand that the way that this has been written, it is certainly not the pure index notation form. Okay, it is not really the index notation form, because in index notation you note that the first rule was that we would not be writing any unit vectors, and these themselves are the unit vectors. So this is certainly not index notation. Okay, whatever it is not index notation. So the rest of the rules of the index notation also does not apply to it. So this is just a shorthand way of representing the various combinations of the unit vectors that may appear in this dot products. Okay. However, what we have written here would be immensely useful further along, as you will see very clearly. I'd also like to mention here something in reference to the very first page of our discussions. So if we go back to our page 1, we had seen that in the component notation we had written our v vector referred to the x1, x2, x3 axis like this, and Alternatively, the same v vector referred to the x1 dash, x2 dash, x3 dash axis in this particular form. We had written this using the summation notation, and that is certainly the correct and the very explicit way of representing it. But what is done sometimes is that this is further shortened and written like this. So this is written as vi ei hat, and this is sometimes written as vi dash ei hat dash. Okay, now you may think that, okay, what's the big deal here? But there is a little bit of an issue that we must be very careful about. The issue is this. You see, if you take a quick glance at it and don't think about it too carefully, then it may appear to you that, okay, here this vi ei hat, it is denoting this particular summation, right? There is no doubt about it. So v1 e1 hat plus v2 e2 hat plus v3 e3 hat. So this seems like we are using this kind of a index, this rule of index notation, that a repeated index indicates summation. So what we had written on the page 2 of our discussions in the previous lecture, this is what it is showing us, that if we have a repeated index, then it implies summation, and it is certainly doing that in this particular case. Now, if we are following one of those rules of index notation, then we would be very much tempted to think of another rule of the index notation, which is that the number of free indices denotes the order of the tensor of that term. So my argument is like this, that if we are using this rule number 2 of index notation, then surely we must be following this other rule also, that the number of free indices denotes the order of the tensor of that term. Now, what happens if we apply that rule? If we apply that rule, then the number of free indices here, how many? 0, because I here is repeated, there is no free index, and that would give us the impression that this entity, this entire term, is a tensor of order 0, but that is wrong. You know that because you see ultimately what is this representing? It is representing this vector, but a vector we know is a tensor of order 1. So what exactly is going on here? You see, this kind of a notation, as I said, there is a little bit of an issue here while writing like this, because it is neither pure index notation nor pure component notation. Okay, I repeat, it is neither pure index notation nor pure component notation, and that is why there is this kind of a confusion. You also note that the moment we write like this, we are violating the very first rule of index notation, which is that in pure index notation we should not be writing the unit vectors, but here you have the presence of the unit vectors. So it is some kind of a hybrid notation. The way that we have written it, it is some kind of a hybrid notation. So if this is so very confusing, why are we even writing this? Why not better stick to this kind of a thing where things are less confusing? Well, we are writing like this because, as you will see, it will certainly make our some of our calculations and some of our initial understanding quite easy as we go along. Okay, so there is a certain advantage to it, but you realize that there is a danger associated to it. So let me just point it out, that when you write some things like this, okay, so there is a little bit of a danger associated with it. So I'm drawing a skull here. Okay, so there's a danger associated here. Okay, we have to be careful here. Okay, so coming back to this, now what I want to do is I want to carry out the dot product, okay, of two general vectors. So maybe the A vector and the B vector. So let's try to do that. I'm taking up this very familiar example of the dot product just to show to you the application of the index notation. Okay, so we want to do A vector dotted with B vector, and what I will do is I will okay, let me first write it out completely in a very easy to understand explicit way, that this is simply this. Okay, and this is and you know that this is simply a1 b1 plus a2 b2 plus a3 b3. We know this. Okay, and you can very well understand that this is simply ai bi. Okay, the moment I write this ai bi, this is pure index notation. There is absolutely no problem with it. You understand that none of the rules of index notation are violated here. We are not writing any summation sign here. There are no unit vectors involved here. There is no free index involved here. There is only one repeated index. The fact that there is no free index present here means that this is a tensor of order 0, which means that this is basically a scalar quantity. And you all know for a fact, even from your high school studies, that the dot product of two vectors is a scalar quantity. In fact, the dot product, another alternative name of the dot product is the scalar product. Okay, but in view of what we have been studying, so let's see if we can approach the dot product in a slightly different way. So again, I'm going to write this, but this time I will adopt the dangerous notation which I had just discussed. So what I'm going to do is I'm going to adopt this particular dangerous notation. Okay, so we have to be a little bit careful. So first of all, I write like this, that ai ei, that represents my a vector. This thing must be dotted with the b vector. Now the immediate temptation is to write like bi ei. Okay, but you see, my ultimate goal here is to end up with some kind of a valid index notation. Okay, I want to end up with this particular result, but in a slightly more systematic fashion. And in order to do that, what I will do is I will not write like this. Okay, I will so even though my initial temptation is to write like this, but you see, the problem here is that this I index, the letter I, is repeated more than once. Repetition up to here was fine, but here it is repeated more than once. In fact, this is written 4 times here, so this doesn't make any sense. So instead of this thing, what I will do is I'll correct this and I will write it with a different letter. So I will write this as bj ej hat. Now if I do that, you see here the ai is just like a scalar component. Okay, it represents either one of these a1 a2 a3s. Similarly here the bj, it represents either one of these b1 b2 b3s. So in terms of the dot product that is taking place, the real thing that is happening with this dot product is basically a game that is taking place between the ei hat and the ej hat. Those are the actual vectors here. So we'll keep the dot with those things and we'll take the ai bj to one side. and we'll write like this: AI hat, EI hat dotted with EJ hat. Now you note quickly that we have already noted down that this EI hat dotted with EJ hat, that is nothing but the Chronicle Delta. So in the very next step, we can write as AI BJ delta IJ. Now there is only one step left, and here we are going to use something extremely useful, which is to uh, take help of the substitution power of the Chronicle Delta. So what is this substitution power? You see, whenever there is anything multiplied with the Chronicle Delta, the Chronicle Delta itself has two indices. In this case, we have I and J. Now, you think of this thing multiplied with the BJ. Forget about the AI here. So when we say the substitution power of Chronicle Delta, what we mean is that so let me just write down here. What I'm considering is BJ delta IJ. So this thing will be nothing but simply BI. So it is as if the result of taking the product of this BJ with the delta IJ is that the index which is not present here and but present in the Chronicle Delta, which is the I here, that gets substituted here. So the J is common here, that J vanishes and this I gets substituted here. So that is what is happening here. Okay, so this thing can be written as AI BI. Now one may question that here we have made the choice of BJ delta IJ. Okay, but suppose we make the different choice, that we write, instead of this thing, we consider the AI delta IJ. Then what will happen? Now you see, it is the index I which is common with the Chronicle Delta, which means that in the this thing is going to be equal to AJ. Okay, so the index which is not present here is the J index, and in the result that J index comes here. So this thing is going to be equal to AJ BJ. Now here I have written with an equal to sign, and you note that if we just go back and check one of the rules of this index notation, so a repeated index is like a dummy index and it can be replaced by any other letter. So we have already written that AIBI is perfectly equal to AJBJ, and it is equal to anything else that may be repeated. Okay, so what we have written here and what we have obtained here using the substitution power of the Chronicle Delta, that is actually being consistent with the rules of index notation. So AIBI is very much equal to AJBJ, and that is, you understand, is equal to A1B1 plus A2B2 plus A3B3. And you see this AIBI is exactly like this AIBI which we had obtained previously. So everything is nice and fine. Now the way that we have proceeded here, even though we lived a little bit dangerously when we wrote these terms, it is extremely useful when we are carrying out higher order tensor operations, as you will see. Okay, in fact it makes our life much more easy, and we don't have to do any kind of guesswork. It comes out very systematically. That is the big advantage of using this thing. Okay, now to finish it off, what we are going to do is we are going to represent the dot product in terms of the matrix representation. So let's do that on the next page. Very quickly, you all know this. So A dotted with B, the matrix representation of that will be this thing. So what I basically mean here is that this is equal to A1, A2, A3. Please note that this T, it represents the transpose. So let me put the transpose here. so that this thing is equal to, we take the transpose of the column matrix, so it becomes the row matrix, and if we actually carry out the matrix multiplication, what we obtain is exactly what uh, we had obtained earlier, a1 b1 plus a2 b2 plus a3 b3. You note quickly that without the use of this transpose, this matrix multiplication, so if we had not written this transpose, this matrix multiplication would have been invalid in terms of the order of the number of rows present, okay, rows and columns present. Okay, so when we are carrying out a matrix multiplication, the first one must have the same number of columns as the number of rows in the second one, so that thing gets violated without the transpose. So everything is nice and fine here. So that's how the matrix representation is, and this of course is very much equivalent to AI BI. Okay, so all these things, these small things that we are writing, this will come in extremely handy when we are discussing the subsequent chapters, and this particular thing is especially useful in the kinematics chapter and the stress chapter, that is the next two chapters. All right, so with this we'll close this part of the lecture, and we'll continue with some other operations involving vectors in the next part of the lecture. Thank you.